Today we're going to review scale drawings and similar figures. You have an upcoming quiz, so we're going to go through some of this stuff to refresh your memory, hopefully to make your score on the quiz better than it would have been. So let's just go ahead. Well, I guess what you should talk about is just right away, what is a scale figure or a similar figure? Scale drawings and similar figures are basically the same thing. You take an original and you either make it smaller or you make it bigger. It's just that you do it in a proportional way. So if you make it bigger, everything is bigger by the same factor. If you make it smaller, everything is reduced by the same factor. So that's what we mean by this stuff. All right, so let's just do some examples since this is review. So for exercises 1 and 2, use the following information. A scale model racing car is 11 inches long, 3 inches wide, and 2 inches tall. The actual racing car is shown at the right. So this is the actual over here. So I'm going to label that just so that it helps me understand what it is I'm talking about. The actual. All right. Let me get back to this. All right. So how wide is the actual racing car? So anytime we're doing problems that involve similar figures or scale drawings, we're typically going to use a proportion to solve this. All right, so what I'm going to do is I'm going to take a proportion, I'm going to make one from information that I know, and then use it to help me find information that I don't know. So how wide is the actual racing car? So I don't know how wide it is. And when we say width, we mean like from the left tire or the tire on the right to the tire on the left, or across the front. Oops, that didn't mean to move. I'm not sure why that's moving, but I should be able to just write here. And I'm not. All right, sorry about the technical difficulty. We got it figured out. So I don't know how wide the car is. Again, how far is it across the front of the car? Now the scale model racing car says it's 11 inches long, 3 inches wide, and 2 inches tall. So I can make a ratio from that, but I have to make sure I use the right parts of those dimensions. I'm looking for the actual width of the racing car. So I know that X is going to be the actual width of the racing car. And the ratio that I can make from the actual car, I know it's 22 feet long. So it's 22, and I'm going to put an L here for long. And X represents the width. That's what I'm looking for. So I know that whatever ratio I make from the scale model, I have to use the width and the length, because I'm looking for the width of the actual car, and the other unit that I know is the length. So I have to use width and length in this problem. So from the scale model, it's 11 inches long, and 11 is going to go in the bottom since length is in the bottom. Long is down here. And it's 3 inches wide, so 3 goes up top because that's the width. I have to make sure I get those units in the right place. Width up top, length in the bottom. Then I can go ahead and just do some cross multiplication here. And when I do that, I'll end up with, let's see, 11x is equal to 3 times 22, which is 66. Then I can go ahead and solve this problem by dividing on both sides. And I'm going to end up with x is equal to 6. And the actual units are in feet, so it would be 6 feet wide. Okay, so again, I set up a proportion using a ratio from the scale model and a ratio from the actual. All right. How tall is the actual racing car? So they want to know from the bottom of the wheels to the top of the car. They want to know this distance. How tall is it? So again, I've got to set up a proportion. So I'm going to have 2 ratios equal to each other. Now they want me to find the height of the car, or how tall it is. So I'm going to put that up here, T for tall. Again, I have to use information from the problem to make the ratio. So the actual, the only unit I know is the 22 feet long. So that's the ratio. This is the ratio from the actual car. Now I have to use the how tall it is and how long it is from the scale model for the other ratio. So I know it's 11 inches long. And as far as tall goes, right here, it says 2 inches tall. So I'll put the 2 up here, and that's tall. Then I can go ahead and cross multiply to solve this again. So I get 11x is equal to 2 times 22 is 44. Divide both sides by 11. And I'm going to get x is equal to 4 feet. Again, I set up a proportion. One ratio, this ratio from the scale model, and this ratio over here from the actual car. And I was able to find that missing information doing that. Let's go down to the bottom here. What is the scale of the model? Well, when we're looking for the scale of the model, what we're doing is we're comparing one measurement from the scale model to that same measurement on the actual. So let's just go with, since we know that the actual is 22 feet long, we're going to compare the length of the scale model to the length of the actual, but when we do that, we're going to put it as a ratio. Well, it doesn't have to be a ratio. I guess we'll just do it with a semicolon or a colon to start. But it could be as a ratio, as a fraction. So I know that the scale model was 11 inches long. So I know I have 11 inches for the scale model, and the actual car was 22 feet long, so 22 feet. You'll notice that in a scale, the units are different, inches and feet. All right, that's what a scale is going to give us. The measurement of the scale model compared to the same measurement on the actual. Now, I can simplify this by dividing both sides of this by 11, and I'm going to end up with 1 inch is equivalent to 2 feet. What does this scale mean? That means 1 inch on the drawing corresponds to 2 feet on the actual car. All right, so 1 inch on the scale model is really worth 2 feet on the actual car. All right, now what is the scale factor? Scale factor is just a little bit different. That just means a scale with the same units. All right, so I'm going to start with my scale over here. And I'm going to take this and move it over to here. Anytime I'm going to get a scale factor, I want to write down my scale first. 1 inch is worth 2 feet. And then what I want to do is I want to change one of these numbers so that the units match up. What that means is I'm going to keep 1 inch over here. And on the right side, I want to say how many inches is 2 feet worth, because I want inches and inches for both my units. So I want inches over here too. Well, I know that every foot is worth 12 inches, and I have 2 of those feet. So I'm going to have 2 times 12, which is equal to 24 inches. So 2 feet is worth 24 inches. So now that my units are the same, we can just go ahead and drop them. And so the scale factor means that 1 unit on the scale model is worth 24 of those same units on the actual. So 1 inch on the scale model is worth 24 inches on the actual. Okay, so that's the difference between scale and scale factor. Scale has different units. Scale factor has same units, which we then drop in our final answer. All right, let's do one more of these examples. So in photography, for exercises 3 and 4, use the given information. James wants to enlarge a photo that is 6 inches wide and 4 inches tall so that it fits into the frame shown. So here's our frame. This is the actual. All right, that's the actual. So number 3, how tall must the frame be for the picture to fit? So we want to know this dimension right here. How tall is the frame? Okay, so if I want to know how tall the frame is, that is going to be represented with X. Well, the measurement that I do know from the frame is 30 inches, and it's 30 inches wide. I'm going to put a little W here, and next to the X, I'm going to put a T for tall. All right, that's 1 ratio. I'm setting up a proportion to solve this. All right, now this is the actual side over here. This is actual. And on the left side, we're going to have the scale. In this case, we'll call it a scale drawing, since it's a picture or a photograph. Now, the photograph is 6 inches wide and 4 inches tall. So I'm going to make my ratio from that. And tall is up top, so 4 inches goes up top. That's tall. And 6 inches goes on the bottom because that's wide. All right, make sure the correct numbers are in the correct positions based on which measurement it is. Then I can just go ahead and do my cross multiplication and get 6 times x is equal to 4 times 30 is 120. Divide both sides by 6, and I'm going to get x is equal to 20. And what was my unit? My unit was 20 inches because the actual is measured in inches. All right, number 4. Suppose James cuts 1 inch from the width of the photo so that it is 5 inches wide before he makes the enlargement. How tall will the frame have to be for the picture to fit? So we know now that the picture is going to be 5 inches wide, but it's still 4 inches tall. All right, we get that information, the 4 inches tall, from the original problem. So that part didn't change, only the width changed. So now it's asking how tall will the frame have to be for the picture to fit? So if we had to change the dimensions of the frame, what would it now be? Well, since they're asking for the height of the frame, that's the tall part. The measurement I know from the actual frame is 30 inches, and that's the width. So for my ratio for the picture, I have to make sure that I have tall in the top and width in the bottom. Well, it's still 4 inches tall, but now the width is only 5. So we're going to cross multiply, and I'm going to get 5x is equal to 120. If I divide both sides by 5, I'll get x is equal to, let's see, is that 24? And the units would still be inches. So it'd be 24 inches. Sorry, this is supposed to be an x here. So x is equal to 24 inches. Now, what's not on here is asking you about the scale or the scale factor. Well, if I was to ask you what is the scale, I would look at this and I would say, okay, well, let's compare measurements from the scale drawing to the actual, the frame, from the picture to the frame. Now, what could I compare? Well, I know the frame based on the picture was 30 inches wide. And I know that the picture originally was 6 inches wide. So I could try to do it with that and say 6 inches wide on the picture corresponds to 30 inches wide on the frame. When I look at this, I see that inches and inches are the same unit. So in essence, I'm not really finding scale, I'm finding scale factor, because scale factor means the units are going to be the same. All right, so you might be asked to find the scale of this, but what we're really asking is the scale factor since the units are the same. So I see that I have 6 inches is worth 30 inches. I can simplify this by dividing both sides by 6, which means 1 inch is worth 5 inches. That means 1 inch on my photo is going to be worth 5 inches on the actual frame. All right, so just wanted to show you there. And then we would get rid of these inches and just have 1 to 5, which basically means 1 unit on the photo is worth the 5 of those same units on the actual. Okay. I think we're going to, let's just take a look at number 6. That'll be our last example of this. A blueprint for a house is shown below. If the front of the house is actually 30 feet wide, how tall is the house? So this is the blueprint. All right, obviously a house is not really 12 inches wide and 14 inches tall. So what they want us to do is find out how tall is the actual house. They tell us it's actually 30 feet wide. All right, so when I set this up, I want to know how tall the house is in actual house. So X is what I'm looking for. What they did tell me about the actual house is that it's 30 feet wide. Again, I'm setting up a proportion to solve this. From my blueprint, I know I need to have tall in the top and I have to have wide in the bottom. So the ratio from the blueprint, tall is 14 inches in the top and wide is 12 inches. And then we can go ahead and cross multiply. And I'm going to get 12x equals 14 times 30. So we're going to go ahead and punch that in a calculator. And when we get that punched in the calculator, it equals 420. If we divide both sides by 12, so I'll do that in the calculator as well, and 420 divided by 12, sorry, x is equal to 35 feet. So the actual height, or how tall the house is 35 feet. Again, we're going to use a proportion to solve all of these types of problems. All right, I'm going to skip this scale map one, and we're going to go to similar figures. So what is a similar figure? Same thing as a scale drawing, really. We're just looking at one figure. And a similar figure is the same shape, but we've changed the size. We either made it bigger or we made it smaller. All right. What do we know about similar figures? Again, they same shape, but have a different size. But one thing, especially with geometric figures like these triangles, what we do know is that corresponding angles that are in the same position, like 55, these two angles are in the same position. Angles that are in the same position are always equal. So 61 is equal to 61 over here. 64 is equal to 64 over there because they're all in the same position. Those are called corresponding angles. Corresponding sides are sides that are also in the same position. So this side here, AC, is in the same position as XZ. So those are corresponding sides. So that's what corresponding means. They're in the same position. Similar to when we were doing parallel lines and transversals, corresponding angles meant same position but at a different intersection. These are in the same position but they're on a different figure. So what are we going to do with these kind of things? Using similar figures. So we have this parallelogram, ABCD. This little symbol here means is similar to. Parallelogram EFGH. Find the value of x. Well, because they're similar, we know that they are proportional. Okay, and when they're proportional, we can use proportions to solve them. So that's what we're going to do. So we're going to set up, excuse me, a proportion. And what we're going to do is we're going to make a ratio from these two numbers. So side AB has a length of 16. So what I'm going to do is I'm going to write AB on the top. Side AD has a length of X. That's the side we're looking for. Okay? So what I need to do is in my other ratio from the other figure, I have to find the corresponding sides. So the side that corresponds with AB has to be in the top. And the side that corresponds with AB is going to be EF, which has a value of 24. And in the bottom, the side that corresponds with AD, right here, this side one, will be EH, this side one. So EH is the corresponding side, and 18 would go in the bottom. Then we can just go ahead and do cross products, and I'm going to get 24x is equal to, I'm going to have to punch 16 times 18 in my calculator. And that is equal to 288. We're going to divide by 24 on both sides. And we're going to get x is equal to 12. All right, so x is equal to 12. So again, we're only able to do this because they told us these are similar figures, and we know that similar figures are proportional. So again, when we're dealing with similar figure problems, we're pretty much always going to be using a proportion to solve it. Let's take a look at just a couple more of these. So the triangles in each pair are similar. Find the missing length, round to the nearest tenth if necessary. So let's look at the first example here. So I'm going to use a proportion to solve this. I'm looking for y. In this triangle, I'm going to use those numbers to form a ratio. So I'm going to say 3 centimeters over 4. Now, when I look at the 3 centimeters, I see that that's kind of, sometimes you get a little tricked up because they'll turn one of the figures so that everything doesn't line up nicely. So you got to kind of look at the side lengths and make sure that you're matching up the ones that appear to be the same length. Now I see that this 3 is on the the side of the triangle, so the y is on the side of the triangle. So I want to make sure that the 3 and the y are in the same position because they're corresponding. So that would mean y would go up top. And since 4 is on the bottom part of this triangle, 12 is on the bottom part of this one, so 4 and 12 should be in the same position, right? Because they're corresponding. And then we can go ahead and cross multiply. So I'm going to get 4y is equal to 36, and if I divide by 4 on both sides, I'm going to get y is equal to 9. One last one. So again, they took one of these triangles and they kind of flipped it so that they're not lined up the same way. So you got to be careful when you make your proportion. So from this triangle, I have 8 and 7. So it's just 8 over 7. From the other triangle, Z is corresponding to 8 because they're both on those downward slanted lines. So I'm going to say Z is up top because these two are corresponding. And then the 5 and the 7 are at the base of the triangle, so I'm going to put 5 and 7 on the bottom because they're corresponding. And then when we go ahead and cross multiply, I'm going to get 7Z is equal to 40. I have a feeling when I divide by 7 on both sides that I'm going to end up with a decimal. So 40 divided by 7 equals, yep, that's a decimal, and we're going to round it to the nearest tenth. So Z is equal to 5.7. All right, so similar figures, scale drawings, all pretty easy stuff as long as you understand how to solve a proportion. All right, we're going to do one shadow type problem, and then I think we're going to be finished here. So a tree casts a shadow 10 feet long. A 5-foot woman casts a shadow 4 foot long. The triangle shown for the woman and her shadow is similar to the triangle shown for the tree and its shadow. So how tall is the tree? So basically what they're asking us to do is find this value here. How tall is the tree? That part of the triangle, okay? They told us that they're similar, which means we can use a proportion to figure this out. So from the smaller triangle, I have a 5 and a 4. So I'm going to set them up as a ratio. The 5 and the x are corresponding. They're in the same position. So I want to make sure they're in the same position in my proportion. And the 4 and the 10 are in the same position, so I'm going to put the 10 in the denominator just like the 4 is. Then I'm going to go ahead and cross multiply, and I'm going to end up with 4x is equal to 5 times 10, which is 50. I'm going to divide by both sides by 4, and in my calculator, I'm going to get 50 divided by 4 equals 12.5. And since we're talking about how tall the tree is, it's 12.5 feet. Okay, so that's a typical example of a shadow problem where similar triangles can help us solve the problem. All right, that was the last problem that we're going to go over. After watching the video, if you still have some questions, please make sure to ask me during class, and I'll be happy to give you some additional help.